Hello and welcome back. In this video, we'll be talking about how to name ionic compounds that contain multivalent metals. Last lesson, we talked about naming ionic compounds that were just binary, and that has a cation and an anion. And for those compounds that we were talking about, if we go back to the page that we were on, these cations just have one charge. So magnesium's always going to have a +2 charge. But if you're looking at your periodic table, you'll notice that some metals have more than one charge that they can make. Here's titanium, for example, which can have a 4+ charge or a 3+ charge. We call these multivalent metals. Multivalent metals can form two different ions. Another example, iron can produce two common ions, iron 3+, which when we write it, we call it iron with the Roman numerals 3, and iron 2+, which we call iron 2. The most common ion is always going to be the top one. So if we're looking at iron 3+ is more common than iron 2+. For compounds containing multivalent metals, you must indicate which ion is present using Roman numerals. If you're not familiar with Roman numerals, then you only really need to know how to count to 5. The Roman numeral 1 is the letter I. The Roman numeral 2 is 2 I's. Roman numeral for 3 is 3 I's. Roman numeral 4 is going to be an I to the left of a V. And the Roman numeral for 5 is a V. 4 is an I to the left of the V because it's saying 1 before 5, which is 4. And then for 1, 2, and 3, you're just counting up how many I's there are. If we're naming these compounds, we have to figure out which iron we're talking about. If you're looking here, we have iron as our metal, as our cation, and oxygen as our nonmetal, our anion. Now the question we have to ask ourselves is, what's the charge on this iron? Because in order to give this ionic compound a name, we need to know the charge on the iron. The way you figure this out is by using the charge on the anion. Oxide is always going to have a -2 charge. If you look at this compound, we have one oxide. Therefore, this compound has a total negative charge of 2-, which means it must have a total positive charge of 2+ in order to counter that. I'm going to write that in words, just so if you're looking back at your notes, that will make sense to you. The charge on oxide is always 2-. This compound has one oxide, so it has a total negative charge of 2-. Because the ionic compound is neutral, the net charge must be 0. The net charge must be 0, which means the total positive charge must be 2 positive. So let me walk you through that logic one more time. The charge on an oxide anion is always 2 negative. This compound has one oxide anion. Because the subscript on this O is not written, we assume there's 1. So the total negative charge of this compound is 2 negative. The net charge of this compound must be 0. So the total positive charge must be 2 positive. This positive charge can be carried by 1 iron ion. This positive charge is carried by 1 iron ion. So it must be Fe2+. Must have the 2+ charge. A good thing to do at this point is to take a look at your periodic table. We think that the iron has a 2+ charge because there's always going to be a 2 negative charge. But if you're a little unsure, check to make sure that the charge that you've picked actually exists. Iron can have 3+ or 2+, so we're good. When we're naming this ionic compound then, we are going to tell the reader which type of iron we have. So the ionic compound formula FeO with no subscripts is telling us that we have iron 2 oxide. It's important to remember that this Roman numeral tells you the charge on the iron, not how many irons are in the compound. There's only 1 iron and 1 oxide in this compound, but the iron has a 2+ charge, so we say it's iron 2 oxide. There's another possibility here, because iron can have 2 charges, and it looks like this. You're still going to start, if you were given this compound with no context, you're going to start by figuring out what's our negative charge. Oxide always has the 2- charge. So for our negative charge, we have 2-, and we have a subscript of 3, which means that this compound has 3 2-. So our total negative charge is 6-. To balance out these 3 negative 2 charges, we only have 2 iron ions. We have 2 iron ions to balance these out. We need to make sure that these iron ions add up to a 6 positive. Because we have a total negative charge of 6 negative. If each iron ion has a 3+ charge, then our total positive charge is also equal to 6 positive. The only way that this compound works is if the net charge is 0. We can tell because oxygen has a negative 2 charge and we have 3 oxides that we have a total negative charge of 6 negative. In order to reach a net charge of 0, our 2 iron ions must balance out our 3 oxide anions. So we must have 2 3+ charges. Because we have iron 3+, the name for this particular compound is not iron 2 oxide, but iron 3 oxide. There's a few here for you to try out. Try to figure out what must be the charge on these compounds. But if we've been given the name, you can try and figure out these two, but if you're given a name, you can work from that. If we're being given the name chromium 3 bromide, then we know right away that our cation must be Cr3+. In our bromide, if you take a look at your periodic table here, my bromide is Br-, just a single negative charge. If we've got a 3+ charge from our cation and a 1- charge from our anion, we're going to need 3 bromides to balance out our 1 chromium 3. So the formula for this ionic compound is going to be Cr for our chromium, Br, and then a little 3 subscript. And because it's an ionic compound, we can also put in that the state is going to be solid. A temptation here is to start using these Roman numerals for things that don't need it. If you go back a few pages, or I guess to the last page, we did not need Roman numerals for any of these, for sodium, lithium, zinc, silver, aluminum, strontium. The reason we didn't need Roman numerals for those is because their ions only have one option. The Science 10 periodic table is nice because it tells you that you need to use the Roman numerals for these multivalent metals. But if you were giving a compound that has tungsten in it, tungsten just has one charge, so you don't need to do tungsten and then the Roman numeral for 6. Also, if you forget your Roman numerals, they are here. So if you forget that a V is 5+, or V is 5, if you find niobium and you look here where it says niobium V, it also has niobium with the 5+. That will help you remember the Roman numeral for 5. There's some good practice on the next page, and I would invite you to try these questions out, so go ahead and pause this video. And if you're back after trying the questions out, we're going to flip to the next page and we're going to talk about polyatomic ions in ionic compounds. The prefix poly, if you see the prefix poly on something, poly means many. The prefix poly means many. And so this means many. Atomic just refers to atoms. So this is many atoms making up an ion. Many atoms making up an ion. Ionic compounds containing polyatomic ions consist of 3 or more different elements, depending on what the polyatomic ion is. Polyatomic ions contain 2 or more atoms bound together, and they can be a cation or an anion. Truthfully though, there is just one cation to look out for, and I'll show you it on the table in a second. When naming these compounds, you keep the name exactly as it appears on the table of polyatomic ions. That is, you keep the name of the polyatomic ion exactly the same. I'm going to just show you where that table is now. So if you have your periodic table, then on the left side of it, just below the group numbers 3 to 9 and above the transition metal block, is this table of polyatomic ions. If you look through, you'll see that they're almost all negatively charged, with one exception, which is the first one, ammonium. Ammonium is the only cation in this whole box. Everything else is an anion. So only ammonium is a cation. And if we're going to name a compound that had ammonium or acetate in it, then we would say ammonium, and then whatever our anion is, or whatever our cation was, and then acetate. We'll give some examples. You just name them exactly like they are in the box. Some examples of polyatomic ions. Try and find these in the box here. This is going to be OH- is hydroxide, and SO4 2- is sulfate. Most polyatomic ions have a negative charge, which means they behave as nonmetals. This means that they are always written last in the formula. The one exception is the ammonium ion, which we just highlighted. That is our one cation, and that is NH4 plus. That is our ammonium ion. Notice that it ends in ium, kind of like a lot of the metals do, like sodium or potassium or aluminum or cadmium. And so it is going to be written first. Ammonium is written first because we always name ionic compounds with the cation first, then the anion. All right. We'll write a chemical formula and we'll also write a name. Write the chemical formula for calcium hydroxide. Well, we know that ionic compounds are named with the cation first, then our anion. You won't find hydroxide on the periodic table, so you have to search for it in the table of polyatomic ions. If I flip to my table of polyatomic ions, I will search through and try and find hydroxide. It's somewhat alphabetical, but not completely. Might take you a little second to find it, but hydroxide is in the second column, about in the middle, and it is OH minus. So if I'm putting together my chemical formula, I'm going to make sure that I know what my ions are. Calcium is Ca2+, and hydroxide is OH minus. Hydroxide, this O and H together, carry a single negative charge, which means to balance out our two positive charges, we are going to need two hydroxides. It is incorrect to write our formula as CaOH2 because this subscript 2 only applies to the hydrogen. And so, to show that we have two of the hydroxide polyatomic ion, we need to put the whole polyatomic ion in brackets to show that this 2 applies to both the oxygen and the hydrogen in hydroxide. It's an ionic compound, so it gets the solid state. If we're working the other way, this is a more difficult example because it's starting with the polyatomic ion. Usually it's ending. This one actually happens to be starting and ending with a polyatomic ion. You might see this particular formula and think, wow, there's 4 different elements in there. And that's correct, but we have 2 ions. Get used to recognizing that NH4 is a polyatomic cation. And then we have a polyatomic anion as well. We have to search for these in our periodic table. We've got an NH4 and we've got an SO4. So if we go and search for those here, NH4 is ammonium, NH4 plus. There was 2 of them in that formula, so we're looking for SO4 2-. We're searching through here. You'll find sulfate in the 3rd column near the top. Sulfate, SO4 2-. This is our cation, ammonium. This is our anion, sulfate. To name this ionic compound, you simply name your cation, then your anion. So the name for this is going to be ammonium, which is our NH4+, sulfate, which is our SO4 2-. Ammonium sulfate. Sorry, it's behind my picture. Ammonium is this NH4. Sulfate is this SO4. Some notes about polyatomic ions, which before you go to the your turn here, some things to look out for. If it ends in ate or ite, It's a polyatomic ion. That is my hint. My hint is if it ends in ate or ite, it's a polyatomic ion. There are some polyatomic ions that end in ide, and there are some polyatomic ions that end in ium, like ammonium. If you go back to your table of polyatomic ions, take a look through it, and notice that lots of these end in ate, or a lot of these end in ite. There are still some that end in ide, like carbide, or cyanide, or hydroxide, or persulfide. Those ones you'll have to look out for. However, if you see a name for an ionic compound that ends in ate or ite, you can find that polyatomic ion in this table. So if I was given the name calcium ion and a carbonate ion, because this ends in ate, I know to look in my table of polyatomic ions. Carbonate is CO3 2-. The calcium ion is Ca2+. These charges already balance, and so they cancel. We've got a balanced ionic compound, so we can just write calcium and then a carbonate. Because there's only one carbonate ion in this compound, we don't need to put brackets around the carbonate. This is fine, just like this. Some common mistakes, though, is getting these names mixed up. They are very similar to each other. Sulfide is not the same thing as sulfite, which is not the same thing as sulfate. Just like nitride is not the same thing as nitrite, which is not the same thing as nitrate. This is also true for chloride. We'll keep them in blue. These are all anions. Chloride is not the same thing as chlorite, which is not the same thing as chlorate. Similarly, iodide is not the same thing as iodate. And phosphide is not the same thing as phosphite, which is not the same thing as phosphate. Check those suffixes. Check the ending of those words. If I'm going to write in what these are, sulfide, that's S2-. That is the ide ending for sulfur, so that sulfur is an anion. Sulfite is SO3 2-, and sulfate is SO4 2-. These aren't the same thing. They all happen to have the 2- charge, but they're not the same thing. Similarly, nitride, which is N 3-, is not the same thing as nitrite, which is NO2, just a single minus, or nitrate, NO3, with a single minus. Feel free to throw in the other ones on top here, but I didn't give myself a whole lot of room. You'll find that chloride is not the same thing as chlorite, not the same thing as chlorate. Yes, those names are similar. Chloride would be here, just like phosphide is here. And then I mentioned iodide, which is the anion from the element iodine. If you're looking at the table, there is an iodite. I could add that in there as well. And an iodate. Those are not the same thing as iodide, just like there is also a chlorite and a chlorate. There's even a hypochlorite and a perchlorate, which are also not the same thing. So read carefully when you see these names. If you see something that ends in ate or ite, it's a polyatomic ion. There's some good practice here. I would encourage you to try these questions. And for our next lesson, we're going to move away from ionic compounds and talk about the other type of compound, molecular compounds, and how you can name those.